Hello and welcome to this section of the Calculus Derivative Help Tutor. And in this section we're going to conquer the famous chain rule from calculus. It's basically another rule of differentiation that lets you take a derivative of more complicated functions. Don't forget what we're doing here, folks. All we're doing in this class, in this section, in this series of lectures, is teaching you how to take derivatives of more and more complicated functions. At first, we started out with the simple constant, right? Derivative of a constant is 0. Then we talked about simple polynomials. When you have terms added together, you take the derivative of each of those terms. If they have x to the power of some number, we learned how to take the derivative of that. Then we learned how to take the derivative of two functions, that were multiplied together, like x times, square root of x, maybe, or something of that nature, or x times the sine of x. We learn how to take derivatives of the trigonometric functions like sine and cosine and cotangent. We also learned how to take the derivative of when you have two things divided by one another. That's called the quotient rule, when you have something on top of a fraction and another function on the bottom of the fraction. So we've been building the complexity of the functions, but in all of these cases, all we're doing is calculating this derivative, which is simply another function that describes the slope of the original function at every point, which is the slope of the line tangent to the original function at every single point. So don't get too wrapped up in, oh my gosh, it's so hard. It's just that we're going to get into more and more complicated functions, and so we have to have additional tools in our tool bag to do that. So we've learned how to do product rule, quotient rule, addition rule, constants, and all these other things. Now what we're going to do is learn how to use the chain rule, which is strictly applied when you have one function nested inside of another function. That is what it is for. You can read your calculus book all day long, right? But it usually won't tell you in quite so few words what I've just explained to you. The chain rule is really used when you have one function and another function nested inside of that function. That is when you use the chain rule. We'll talk about in a minute why we call it the chain rule. What does a chain have to do with it? But basically it amounts to, you have a box here that's a function. Inside that function is another function. So it's like, you can kind of think of like pulling on links of a chain. One function is sort of connected to the other function. It is dependent on the other function. So to give you a concrete example of what I'm talking about, right? The function f of x is equal to the sine of x squared. Now this would be a function that you'll find out here in a few minutes. You have to use the chain rule to find it, okay? So we have the sine, and we know how to take the derivative of sine. That's cosine, right? And on the inside of the sine, we do not have x. We don't have just a straight x. We have something else. We have x squared. We know how to take the derivative of x squared. We learned that a long, long time ago. So you already know how to take the derivative of the sine function in general. But remember, if you go back to the trigonometric lesson, we were always learning how to take a derivative of sine of x, cosine of x, tangent of x, cotangent of x, secant of x. Nowhere ever in that lecture did I ever tell you it was okay just to apply that to anything other than x on the inside. What if I have sine of square root of x on the inside? Well, that's different. What if I have sine of logarithm of x? We'll talk about those later, but that's different. What if I have sine of cosine of x being on the inside like this? Well, that changes the function, folks, and you can't just use the general rule of taking trig derivatives in this case to figure that out. See, a lot of students will just say, well, the answer to this is cosine of x squared, because I know that the derivative of sine is cosine, right? So I'm just going to keep this in the middle and it's going to be over. So I'm going to say cosine of x squared. Most people would say that's the answer. Well, that's not the answer. It's close. It's close, but it's not the total answer, all right? So what we need to do is use the chain rule to figure out how to do this. So I'm giving you a concrete example. In all of the discussion that follows, I'm going to sort of present the chain rule how you would see it in your textbook so you can kind of relate what you're reading in your book to real life. But I want you to keep in your mind, in your brain, this mental image in your head. It's what I call, your books usually don't call it this, but I call it a nested function. A function, this one being x squared, inside of another function, which would be the outer function, in this case is a sine function. There's lots of examples of when you would use the chain rule for these nested functions. I've given you one. We're going to work a ton of problems. But before I do that, let me give you just sort of a quick description of what you would see in your book. In your book, you would see something like, suppose you have a function. And that function is capital F of x. And your book is going to look a little bit different, okay? So use your imagination. But the way you would see it is some function, and it would be f of g of x. Okay? So that's the first thing that confuses students right there. Like, what does this mean? Well, this is telling you the types of functions that you apply the chain rule to are functions that basically exist when you have an outer function with an inner function nested inside of it as the argument of the outside function. Come back to reality here with an example. Sine of x squared is exactly what I have here, right? I have an outer function and I have an inner function. That's the g of x would be this in this case. The outer function would be the f here, right? So when they're nested, you have to use the chain rule always, right? So this is basically like this. But if you have a function like that, then your book is basically going to tell you then to take the derivative of this big function, capital F, take the derivative, in other words, of this nested function right here, then the way you do it is you say f prime of g of x multiplied by g prime of x. And you see, this is where students also get confused, because when a lot of times, forget about my example up here, a lot of times your book is just going to tell you this, and you're going to be expected to know what the heck they're talking about. But a lot of students, when they read this, it looks like gobbledygook. It doesn't really bring it home. What this is saying is, again, taking our example here, if I'm trying to take the derivative of this, what I have to do, forget about this function, this part right here. What I have to do is I have to take the derivative of the outer function, in this case the sine function, right? And I have to keep the argument, the inside, the same, the g of x. So I'm definitely going to be taking the derivative of the sine function, but I'm going to leave the inside the same. But then after I'm done with that, I'm going to multiply the answer times the derivative of whatever is on the inside. The derivative of whatever is on the inside. That's how you read this. So you say, okay, I take the derivative of the outside function, keeping the inside argument the same, then I multiply by the derivative of the inside. So you see, what I told you when we started, you know how to take the derivative of sine. You know how to take the derivative of x squared. Notice we are using both of these facts in the answer. We're taking the derivative of the outside function and the derivative of the inside function. We're multiplying them together. That's really what the chain rule is. So however many nested layers you have, let me see, I can have some other stuff in here. I can have some other stuff nested inside here as well. You peel back the onion, basically, and you continue taking derivatives, going down and down, deeper and deeper into the inside of the function until you're done, until there's nothing else to take a derivative of. And this will become a lot more clear when we do some examples, but I'm just trying to give you the general notion of this is how you would read it in your calculus book. Now, the other thing your calculus book will tell you, a lot of times it'll be written like this, but it'll also a lot of times be written in a different way that I want to expose you to. So let me show you another notation. This is mainly just for your benefit, right? So that you'll, you'll follow your professor and so you can know what he's talking about. So suppose that I have something, y is equal to f of u. Let me make this a little bit more clear. U. And what if I have that u, this guy right here that's on the inside, is equal to g of x? Right? So what I have here is I have some equation y. It's equal to a function of some variable u. But the inside variable u is in turn equal to another function. So you see, this is just another way to say the same thing that we were just saying before, that you have a nested function. Think about it. If you take u here and you plug it in here, then you're going to have f of g of x, which is exactly what I have up here. That's why I say it's another notation. It's not different. It's just a different way of writing it. So f of u, this function f, depends on something we're calling u, but u in turn depends on g of x. It's the same thing as saying what we had before. But if you write it that way, then if you want to use a different notation, then to take the derivative dy with respect to x, the derivative of this function y with respect to x, is going to equal to dy with respect to u multiplied by du with respect to x, right? Now, I need to make sure you understand what I'm saying here, right? So, I'm just saying it's a different notation. So here I have some equation, it's basically f of u, some function. It's dependent on something inside of here. This something is in turn dependent on x. So this is what really forms the chain in the chain rule, right? You have an outer function dependent on something, and the inner function is depending on something else. Bringing it back to our example, this outer function is dependent on u, in this case would be x squared. U in turn will be dependent on x. So it's just two functions that are kind of placed inside of one another. This is just another way to write the same thing. So to find this derivative, it's the same exact thing as what I've said here. You take the derivative of this outer function y with respect to the inner guy that you had to begin with. This is sort of like what I'm saying right here. And you multiply it, that's where we have multiplication here, times the derivative of the inner function as it relates to x, which is exactly what I've written here. So you've got the same multiplication going on, you've got the same terms, it's just a different way of notation. That's what you'll see it usually both ways in your book. Now notice what we have here. We're going to first see how y depends on u, but then we're going to see how u in turn depends on x. Now if these were fractions, if this was 3/4 times 4/5, how would you simplify this fraction, right? You would say, well, 4 cancels, right? So the answer is 3/5. You can sort of think of these differentials as fractions. They are fractions, really. It's the rate of change of this with respect to this. Notice du is here, and du is also on the top. So really, since I've taken this derivative and I'm multiplying by the derivative of the inside term, the du's can be said to sort of cancel. So what you're left with is dy with respect to dx, which is what I have over here. And that's another reason why it's called the chain rule, because when you multiply these derivatives together, you cancel the differentials that don't really matter in the end, and what you're left with is sort of the final product of how the outer function depends on the base variable that we have. In this case, it's x. So you have this nested function here. Ultimately, we want to know how does this function change with respect to x. So first we see how this function changes with respect to its inner term, and then we see how the inner term changes with respect to x, and we multiply them together. This is the theory to sort of explain graphically why this chain rule works, because of the fact that this cancellation happens. Now, if you talk to a real mathematician, they don't like you to think of these derivatives dy dx as real fractions, because they're infinitesimal derivatives and everything. But you can sort of look at the cancellation in the same manner. I'm telling you, that's going to get you a long way to understanding how derivatives really work. So you need to think of it that way. We're going to do a lot of problems here in just a second. But ultimately, you're looking for a nest. You're looking for a function within a function. And then when you see that, you take the derivative of the outer function, and then you take the derivative of the inner function, right? That's all you do. So let's go and lock it down with some examples, because I'm absolutely confident when you see a few examples, you'll say, oh, well, this isn't that big of a deal. So let's go and do that right now. Let's say we have f of x is equal to 4 minus 3x squared raised to the power of 400. All right, now you might look at this and say, well, I don't need the chain rule for this. Why would I need the chain rule for that? I already know how to do this. This is just a polynomial. But notice that it's wrapped up and it's all raised to another power. So you've actually never done a problem like this before, because here, see, your inner function here is this guy. Your outer function is what we talked about in the beginning of the course, something raised to a number. So you need to think about it like, okay, if this function were, this is an aside over here, if this function were x to the 400, simply just x on the inside, you would know how to take the derivative of this. It would be 400 coming out in front times x to the 399. You subtract one off the exponent. So you know how to take the derivative if this were what we had. Unfortunately, it's not x here. It's something much larger than x. It is a function wrapped inside of this outer function. So the outer function is the 400 raised to the exponent. The inner function is what we have here. So the way we handle it is we say that f prime of x is equal to, we take the exponent, we do the derivative of the outer function first, which is the exponent on the outside. So it's 400. We have to keep the inside the same, 4 minus 3x squared to the 399. A lot of students would leave it like that and say, well, that's the answer, right? Unfortunately, it's not the answer, because you still have all of this stuff on the inside that's part of the function that you haven't really taken the derivative of. So what you do, this is the derivative of the, quote, outer function. You take the result that you have and you multiply by the derivative of the inside. right? The derivative of 4 is 0, so it's just 0. The derivative of this, you take the 2 times the 3, we got a negative here, so what you're going to have is negative 6x to the 1 power, because we subtract 1 off. So you have negative 6x there. So to rewrite it all, f prime of x, what you're going to have is 6 times 4 is 2400 with a negative sign. You'll have negative 2400. You still have an x out here. 4 minus 3x squared raised to the power of 399. This is the answer. Negative 2400x parentheses 4 minus 3x squared to the 399. Make sure you're tying this back to the chain rule so you understand. You have to identify an outer function. In this case, this is the exponent of the 400. The inner function that's inside the box is what we have here. So first, we take the derivative of the outermost thing, keeping the argument the same. 400 times the argument times, we'll raise to the power to 399. Okay? If this were just simply x to the 400, we would have an x in here, we would be done. But since we don't, we multiply the result times the derivative of the inside. In this case, it's just negative 6x, and then that's the answer. Tie that back to what we covered up here. All right, tie that back to what we covered up here. We said the derivative of a nested function like that is the derivative of the outer function with the inner argument intact times the derivative of the inner argument. So it's the derivative of the outer argument, or the outer function with the inner argument intact, times the derivative of the inner argument. That's it. And that's what we're going to be doing over and over and over and over and over again. We're going to be looking and identifying the outer function and the inner function. We're going to take the derivative of the outer times the derivative of the inner. And that's really all it's going to be for the chain rule. You're just going to be getting into more and more complicated functions. So what if I had f of x is equal to the sine of 5x. So again, before the chain rule, a lot of students would say, well, I know how to do this. I know how to take the derivative of sine. That's just simply cosine. Unfortunately, this is not sine of x. So that's the only thing you know how to take the derivative of trig functions up till this point is sine of x. If you have anything other than x in the inside, that's different. So this inner function is 5x. The outer function is sine. So what we're going to do is we'll say the first derivative of this function is equal to the derivative of the outer, which derivative of sine is cosine, so we say cosine. We have to leave the argument intact. But we don't stop there. We multiply by the derivative of the inside. The derivative of 5x, think about it, is just 5. So finally, the derivative is 5 times the cosine of 5x. And that's the answer, 5 times the cosine of 5x. You identify an outer and you identify an inner. And you just go from there. So let's go ahead and ratchet things up a little bit. Let's say we have g of x is equal to tangent to the 6th power of x. Now, in the beginning days of calculus, I want to make sure you understand. When you raise something to a lot of times in books you'll see tangent to the 6th of x. What this is the same thing as tangent of x raised to the 6th power. Instead of writing the parentheses here and then sticking the exponent on the outside, you write the exponent here. You don't want to write the exponent without the parentheses here because then you won't know if it's tangent of x to the 6th or if it's the whole thing raised to the 6th. So a lot of times you'll see the exponent over here, and that just means the whole thing raised to the 6th power. In the beginning days, it's probably going to save you a lot of headache just to rewrite it like this, so that then you'll see that what we have is an outer function, which is this exponential. The inner function is this tangent that we have. So we proceed exactly in the same way. We say the first derivative of this function is equal to, the outer derivative would be 6 times the tangent of x raised to the 5th power. So we keep the argument intact. We're taking and we're bringing the exponent down. We're subtracting 1 off the exponent. If this were simply an x in here, we would be done. It would be 6x to the 5th, but we're not done because we have this tangent here. So we have to multiply by the derivative of the inside. The derivative of tangent is secant squared of x, right? So what we're going to have is, to rewrite this here in the way that you normally see it in the book, 6 times tangent to the 5th of x multiplied by secant squared x. Again, this is tangent x raised to the 5th power. This is secant x raised to the 2nd power. This is what you would typically see how it would be written in a book. So what we have here is we're taking the derivative of the outer function, multiplying by the derivative of the inner function. And that is what we're going to be doing over and over and over in these cases. So what I want to do now is ratchet things up a little bit and give you something that looks a little bit more foreign. F of x is equal to the cubed root of 1 minus sine of x. So this would be the kind of thing you see on a test and you're like, whoa, take the derivative of that, it looks really tough. The first thing I always tell people to do is always rewrite any radicals in terms of an exponent. 1 minus sine of x, in this case it's 1/3. Right? It's just easier because you're going to end up using your rules of differentiation that you know from exponents. So if you leave it like this, you're not going to be sure what to do. But if it's an exponent, you'll know what to do. So the outer function is this exponent. The inner function is what we have here all together. So what we're going to have is f prime of x is equal to. The outer derivative is 1/3. Leave the argument intact, 1 minus sine of x. And then we have to subtract 1 minus the exponent. 1/3 minus 1, if you think about it for a second, is negative 2/3. So this is the outer derivative. A lot of students would stop here if they didn't know the chain rule, because they wouldn't know that they have to multiply the result times the derivative of everything on the inside. The derivative of 1 is 0. The derivative of sine is simply cosine, but I still have this negative here. So what it's going to be is negative cosine x. The negative coming from the negative that's already there. So what you have in the end is negative 1/3 cosine of x, 1 minus sine of x, to the negative 2/3. And that's the answer. Negative 1/3 cosine x, 1 minus sine x to the negative 2/3. But the same thing is happening in all cases. The trick here is really to rewrite the radical so you can see, okay, I have an exponent. Inside is the argument, I have this other function. So I take the outer derivative and multiply by the inner derivative. Right? So let's work with some trigonometric functions here. Let's say we have g of t. Let me make g of t a little bit more clear. Let's say we have cosine of sine of t. So this is pretty clear that this is a nested function. The outer function is the cosine function. The argument is another function. It's the inner function, right? But you apply it exactly the same way. G prime of t of cosine is negative sine. So it's negative sine. You have to keep the argument the same, sine of t. Right? That's where most students would stop. Take the derivative of here and they would leave the argument the same. But you have to multiply by the derivative of the inside function. Derivative of sine is cosine. So it's you multiply by cosine of t, and that's the answer. Negative cosine t times the sine of t. And that is the answer. Now that looks like a weird function because you have, and if you want to make it clear, you can wrap parentheses around this. So it's cosine t times the sine function, but the argument of the sine function is another sine function. So it looks a little bit weird, but think about it. You can put this in a calculator. It's not, there's nothing preventing you from throwing this in a calculator and getting the answer, having the sine. You can have the sine of 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 t. That would be like 5 or 6 nested sines. You would have to continue multiplying by the inner and inner and inner function each time. And we'll get there. We'll get to some more complicated ones as we go along here. All right, our next function is f of x is equal to x minus 1 over x plus 1, all raised to the 3rd power. Now I'm not gonna lie to you, this is a little bit complicated. I mean, you have something that I can tell you right now is gonna be a little more complicated because the outer function is this exponent. The inner function is kind of nasty because you've got this fraction going on in there. And we know from before that when we have fractions like that, we're probably going to end up using the quotient rule. And if you remember back from the quotient rule, that's kind of involved by itself. So you have to deal with the nesting going on, plus you have to be really comfortable with all of your previous definitions and uses of derivatives so that when you get to multiplying by these inner derivatives, you know what you're doing, right? But the trick is 2 things. 1, please don't skip too many steps, especially in the beginning. If you try to take these derivatives in your head and write them down, you're just going to make a mistake. And number 2, show everything that you can on your paper. so that when you go back and make a mistake, you can see what you're doing, right? So I'm going to show you how I really do write it out, each and every time, so that you can see, hopefully to build some good habits. So f prime of x, the derivative is what we seek. The outer function is this exponential. So what you're going to have is to bring the 3 down, keep your argument the same, x minus 1, x plus 1, and that's raised to the power of 2. But what we're going to do is multiply by the inside derivative, x minus 1, x plus 1 derivative. This is my derivative mark. I'm trying to lay it out and show all of my steps. A lot of students would do this, and then they would immediately start taking the derivative here. And once you get good at derivatives, you can write your derivative out in the same line. But it's important in the beginning for you to write it out and break it out so that you won't make any mistakes. So that we have the outer derivative multiplied by the inner derivative. Then in the next step, take this inner derivative. Then in the next step, simplify everything that you have so that you can then look back and see what you have. So f prime of x is equal to 3 times x minus 1, x plus 1 squared. And what do I have inside here? I have the bottom, x plus 1, times the derivative of the top, which is x minus 1 prime, minus the top times the derivative of the bottom. And all of this is divided over the bottom squared, x plus 1 squared. So again, I've chosen to be explicit. Bottom times derivative of the top minus the top times the derivative of the bottom over the bottom squared. I could have chosen to take these derivatives in place as I were going along. After a few months of calculus, you can probably do that without worrying too much, especially because these are pretty easy derivatives. We'll see in a second. But in the beginning, you see, you've got a nested chain rule, and then when you do this quotient, you've got derivatives you're taking all over the place. If you try to do it all at once, you're going to make a mistake. It's just going to be a matter of time. So let's hope that we don't make one here. So what we're going to have is f prime of x is equal to 3 x minus 1, x plus 1 squared. Okay? And on the inside, on the top, we have x plus 1. And then what we're going to have for this derivative, the derivative of x is just 1. The derivative of this is 0. And then over here, we're going to have x minus 1. And the derivative of this x is 1. The derivative of this is 0. So we see it; those are quite easy derivatives to take. X plus 1 squared. Close our bracket off. So we can look back and easily see, okay, this was the derivative. Okay, we did these derivatives. Okay, that's what we have. Next, we're going to go and simplify. Let me try to alternate colors to try to break it up here. F prime of x is equal to 3 x minus 1, x plus 1 squared. On the inside, this is just multiplied by 1, so what we're going to have is x plus 1. This is just multiplied by 1, so it basically disappears. We'll have minus x plus 1 on the top, and then over here we'll have x plus 1 squared. All right, so what we have is a cancellation here. We have x and a minus x, so those are going to go out. So we'll have f prime of x is equal to 3 x minus 1, x plus 1 squared, open brackets, and then the x's are going to go out, so what we're going to, because this will cancel with this, so we'll have 1 plus 1 is 2, 2 over x plus 1 squared, right? 2 over x plus 1 squared. And then finally, putting it all together in some final cohesive answer, f prime of x is equal to, this 2 times this 3 is going to give us 6, right? And then this is a fraction that's all squared. So the top is squared and the bottom is squared. So on the top, you're going to have essentially x minus 1 squared. That comes from the numerator squared. On the bottom, you're going to have an x plus 1 squared. Here's another x plus 1 squared. You can combine these two terms to give you x plus 1 to the 4th power. The bottoms are the same, so you just add the exponents. So you have 6 times x minus 1 squared over x plus 1 to the 4th power, and that is the final answer. So, it was a few steps, but, there are lots of problems in algebra that are even longer than this, and we've actually shown every single step. We take the derivative of the outside, subtract 1 from the exponent, times the derivative of the inside. The inside derivative happens to be a quotient, so we do bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Here we take these very simple derivatives. Here is the answer After this is just algebra. We multiply this out, we cancel terms, we get this, and then we simplify and combine it all together. So here we have done quite a few good problems to illustrate how to use the chain rule. Very solid, giving you some good bedrock and some good problems to give you confidence to know what it's about. Outer function, inner function. Remember that. That's what the chain rule is. We're going to go ahead and stop the section now. Practice these if you need to. Practice extra problems. In the next section, we're going to continue working problems in the chain rule. I'm going to ratchet up the complexity a little bit so that these inner functions get even more complicated, because in real life, that's what you're going to work on your test. You're not going to usually be given a super simple problem. The inner guy might be a real bear to deal with. So what we're going to do in the next few problems is have a few challenging ones to show you how to keep it all straight and get yourself down to the correct answer every single time.